Okay, where are you? There you are. All right.
That's the question. By putting something on entry dollars. Yeah. So the easiest thing was to plan an output. And yeah, they were and apple cider, good apple cider apple service. How did that happen? So the program is called Flubber. They used to make this drink called Flubber. They would eat a hot poker with fire. This kind of fireworks they warm house. You eat a hot poker, or I listen to hot cider. Maybe this Robert's on board stuff. Yeah, but I think that's really like for a while. That's yeah, just like it wasn't on the cider or crusher, that's why you need to yeah. There's a lot of water there. Got it.
Dr. Ting, anytime you're ready.
Anytime, okay. 30 seconds.
Let's see. This one is on.
So the spelling checker thought it'd do better as to their viral coefficients.
Hmm?
I said, your spelling checker has to be overridden.
Those coefficients are just getting viral now.
Yeah. It's all on YouTube.
Okay. All right.
Stop.
All right. Let's get started. Hello. Welcome to the Silicon Valley Fourth Interest Group. And I'm C.H. Ting. And I've have the good fortune to talk about this second and third Virial coefficients. It's not force related. It's completely thermodynamics. But I thought that there's something interesting for you guys because I did it all with spreadsheet, with Excel spreadsheet. So that's you might, if you are not familiar with the Excel, you may learn something today. Let me see. Let's go down. Okay. Summary. Talk a little bit. My talk kind of mixed up, so it's not completely in this order. So I talk about research on Google, research with Excel, and then the main topic is the Virial equation of state. And the main focus is on the third Virial coefficient. and I've used 3 different methods to compute third Virial coefficient of argon, which is a very standard gas for all thermodynamic studies. Oh, it's very noble. It's very noble, it's very inert, and it's a very good, good model of molecule because it's not too small. If the atom is too small, there's a quantum effect, which kind of distort lots of things. So it's big enough, but it's not that big, and it's not cannot be handled very conveniently. And I guess it's also cheap among the real gases. So the main point I want to make is the correlation between the Virial coefficient, especially the second and third Virial coefficient. I make some conclusions, or I will also do a little demo with the spreadsheet to show you how things can be done. Yes?
I didn't catch what is the data we're working on.
Okay, I will talk about the data. It's on argon, the pressure, volume, and temperature data, and it's the analysis of this data which I'll be talking. Okay, so last month, I will present this cubic Virial equation, and my goal to study this equation in this form is so that I can expand it or modify it, so we can present solid, liquid, and gas equilibrium. And I don't think it has been done, because most of the equation of state study concerns mostly the gas phase and sometimes the liquid phase, but never, ever was anybody can write an equation and show that there's a solid phase coming into the play. Okay, so that was the last month's presentation. So the cubic Virial equation, I use this equation, well, with lots of reasons, but in order to compare this Virial equation with the standard data that's been presented, the best way is to analyze the compressibility. Compressibility is defined as PV divided by RT for 1 mole of gas or molecules. So the Z, if you know the ideal gas law, the compressibility is just 1, because the PV is equal to RT. Okay, and the real yeah, it's 1 mole for 1 mole. And if it is a real gas, then it deviates from this ideal gas law. And then you add into some correction terms. And then so that's the Virial equation. So you just expand the deviation in terms of the inverse of volume or density. Mm-hmm. So most of the studies on gases are done on compressibility, because it's compressibility is dimensionless, and it applied quite generally to all different gases. So last time I showed this Z plot. So if you plot Z against the pressure, you get these nice curves, and you see here there are 10 different gases, and they follow pretty much the same same curves. So this is the Z plot from experimental data. So I use my equation of state and I plot Z. It kind of gives you the general trends, but not quite, not very accurately. But the trend is there. So what you need to do is modify this equation to get the okay. So the to make the data fit, make the equation fit the data, I need to correct or scale these two terms by t square. Okay, because it already has an RT in it, so it becomes a T cube. If I scale this this equation by a factor of T squared, then the Z plot are brought to within 5% of experimental value. So this is the best plot I can generate with my equation of state. And it kind of it deviates a little bit. For example, it dips down to 0.2, and I have it, you know, about 3% off. So I think I have the general trend correct if I scale the equation properly. But the second Virial coefficient, the second term and the third term are scaled together. So that Z plot is above the critical temperature. Below the temperature, gases start to condense. And to explain or to account for the gas-liquid equilibrium accurately, I need to scale this these two terms by a factor of t square root of t. Okay, why? I don't know. It's just that I try to fit the data, and you need to scale the equation. And if you scale the equation properly, like here, then the isotherms. So these are the PVT plots. Came out very nicely, and then those inverted four curve, and these curves are the Gibbs free energy of the gas. And the interesting thing about the Gibbs function, Gibbs free energy, is that the curve comes down and goes up and comes down again, and where it crosses, and that's where gas and liquid comes into equilibrium. And at the crossing point, if you make a horizontal line to the left, then you can find the saturation pressure at that particular temperature. So this equation, if I scale it properly, it will produce the very quite accurately the equilibrium curve isotherms for gas between the critical point and the triple point. The triple point is where gas, liquid, and solid comes into equilibrium. So that was the last month's presentation. So I was thinking of writing a paper and submit it to a reputable journal like Nature or Science or something like that. But in the process, I was thinking, is there any hole in the paper that people can find and shoot me down? And I think the biggest problem with my equation is that second and third virial coefficients are highly correlated. So these two terms have to be scaled together, okay? The second virial coefficient and the third virial coefficient, they have to move together in order to account for the real gas behavior above the critical point and below the critical point. And this is not, this does not agree with the current literature, okay? And in the current literature, people studied for 100 years these coefficients in full virial equations. And if there's very little controversy in the second virial equation. And this basically is the slope. If you plot z against the density, it is the slope of the curve. And lots of people measured it for almost lots of different gases. And the second virial equation, second virial coefficient comes out very nicely, very accurately. The third virial coefficient is very different because it's the third and it's very difficult to get to, difficult to compute. So typically the data, for 100 years, people have studied the real gas behavior with the virial equation. And there's a big compilation of second, third virial coefficients for all different gases. And all existing studies show that these two virial coefficients are not correlated. They have basically no relationship to each other. So I thought, well, pick argon as a standard molecule to get experimental data. And I want to look at the real data and see how these things were derived. And then before we can make any conclusion. So this is a very typical drawing of the argon. And it's second virial equation. So it is interesting in that about the 400 degree Kelvin, the second virial coefficient becomes 0. And this is called the Boyer temperature. Because at that point, this gas behaves almost like ideal gas, because the second virial coefficient is 0, and this curve is basically flat. So above 400, the second virial coefficient goes positive, and below 400, it decreases very rapidly. Okay. So this is the behavior of the second virial coefficient. But the third virial equation, it kind of decreases towards high temperature. And this is about the critical temperature. And below critical temperature, it drops. So all different gases behave the same way. If you, I went to the literature and look at all the second and third virial coefficients, and they are very consistent, and they all reported this way. There are even big books compile the second and third virial coefficients for all different molecules. So, if I'm right, they are wrong. Okay, how do I prove? So to substantiate my paper on the cubic virial equation, I have to prove that 100 years of research is wrong. So the best way is to go back to the original data and to see how these data were derived. And it's better to go back to original experimental data to make a very strong statement, one way or the other. So, you know, I was sick for the last last 5 months, and I should have come to Stanford and go to the library and then read all the go through the library, read all the journal articles, and do all this research. So when my wife didn't allow me to get out of the house, so all I can do is Google everything. Okay, and so I found 3 very big compilation of data on argon. And they cover a wide range of temperature, a wide range of pressure, and they have. So the biggest paper is this one from the Bureau of Standards. You know, Bureau of Standards has a whole laboratory devoted to cryogenic research, and they collect all this data for all different molecules. And the number 7 is specifically on argon. It's in 1969. And in 1989, there's another, people publish lots of this data in the Journal of Physical Chemistry Reference Data series. And in 1989, there's a big compilation. And in 1999, another big compilation came out, which is which they want to substantiate another equation of state. So I picked this. I have copies of all this. They are all on the PDF files. So I look at all these things and pick this one for my study, because this one is really old. 1969, the data are printed with line printer, and then these guys specifically mention that all our data we build the very substantial Virial equation. So they calculate all this data and then print out them in big tables. But because these data are calculated, not the original data, so they actually put them on some background, and the background makes the pages look awful. You can't scan them. So this one has a very large collection of data, and the printing is, it's 89, and the PDF file looks much better. And so I scan all the data in this paper, and it has about 150 pages. I don't need all the data they published. I only need the density or volume data. So I use OCR to read the paper and then extract the data from the density, basically pressure, density, temperature data, which I call the P-rho-T table. And this table, when you OCR the OMNI page, the OCR is from OMNI page. And after they recognize the characters, they kind of try to figure out what the source, what's the meaning of data in the source. And they found, oh, here is a table. So they threw out the data in spreadsheets. So that's very nice. Okay, and I imported them into Excel. So the main data, P-rho-T data, has 116 rows for temperature and 44 columns for pressure. So it's a very large coverage from triple point, which is 83 degree Kelvin, to 1200 degree Kelvin. and the pressure from, from 0 to 1,000 MPa, okay? So it's about 1,000 atmosphere. So very large coverage. And so, to analyze this data, my equation is non-standard, okay? So I have to cast them into this form. So I can use existing data and compare the results of the analysis, okay? So the main table is at various pressure, various temperature, you get the data for rho, for density. And then we have to analyze the density, the pressure density relation, use this equation, or use the compressibility equation. This is the main equation to analyze. If you account the data, convert the PVT data into the Z, and then you can analyze it with this very second order polynomial. So Z is dimensionless. It is good function for second order polynomial regression analysis. Okay, spreadsheet actually has this capability. So it has polynomial regression. You go into you select the data, go into the regression analysis, and it would ask you what do you want to do. You can pick a polynomial, and then it defaults to second order. But you can pick the second, third, however many terms. So my study is concentrated on these three terms, okay, and the second order polynomial regression analysis is the proper tool. Yes. Say it again.
You're doing a linear least squares fit of this quadratic
yeah,
thing.
it's not linear. Linear is first order regression. Second order regression is quadratic.
Okay.
Okay.
Right. Yeah.
Mm-hmm.
I just want to make sure you're.
Right.
But you're
So,
doing linear least. I mean, you're doing least squares.
Yeah, it's the first order is called linear regression. And if you extend it to second term, it's the second order polynomial regression analysis, okay? Okay, actually spreadsheet, Excel can solve BNC almost automatically. Okay, so I scan everything into the Excel. That's a P row T table. And from the P row T table, I can generate the PZT table automatically with this Excel array formula. Okay, so if you you have the main table entered into C2, which is the upper left corner of the entire array. Okay, and C1 is the row of pressure, and then A2 is the column of temperature. So this way, you basically what you say is you take the pressure, divide by the universal gas constant 0.008314, and divided by temperature, and then divided by the density. Okay, so that's Z. That's one cell of Z. But then the Excel has one nice feature. I don't know if you know, it's called the fill handle. Okay, the fill handle is a little cross in the lower right corner of a cell. You press on it, it turns into a big plus, and you drag it along. And then you drag it over the entire table, and it fills the entire table with new data according to this formula. And here there's a dollar sign in front of a symbol. Specify that symbol is absolute. Okay. Without a dollar sign, it's a relative reference. Okay. So C2 is a relative reference, and it will refer to the entire table from C up to AZ, and from 2 up to 117. Okay, so it covers entire table. So this is the way to mark. I think invert the table, invert the data, so you got the volume. Okay, and take the pressure and divide this thing, and then divide the temperature. So in one simple equation, you do the entire, you convert the entire array of P rho T into the PZT. The P rho T and PZT table must use together to extract second order polynomial. So we got this array, and we got a row array. So between these two arrays, you can do regression analysis. Okay, so this is the upper left corner of the P rho T table. Okay, so here we have temperature, and on top it is the pressure, and then the data. Data are all in density. Density in the in terms of moles per decimeter square, and that's a very convenient unit to handle the data instead of volume. Volume is sometimes getting very big. Okay, so this is the PZT table. Notice that in the first cell, I have this array formula. And if you enter that array formula into the first cell, and then see the little dot at the lower left, lower right corner, if you use your mouse and drag that little cross across the whole column, and whole column gets filled up. And if you drag this one, the whole column over to the right, and you cover the entire table, and you generate, it fills up the entire table with the compressibility data. Notice that the compressibility is very close to 1 at the lower pressure, higher temperature range. Okay, and it gradually getting smaller and smaller and smaller to the left, to the right. Any question? Okay. So Excel can do many types of regression analysis. My interest are in the second order polynomial regression, specifically solving B and C for my cubic Virial equation of state. But results of regression analysis heavily depend upon range and accuracy of selected data. Basically, it's range. You know, if you select different range, you get different results. And here is the example. I took the data at 120 degrees Kelvin, and that's between somewhere midpoint between the triple point and the critical point. So here I listed the data, the density data in this column, and then the compressibility data on this column. So what I want to is to derive the B and C coefficient for this for the compressibility equation. You see here, from the top down, okay. So it is very small, and it becomes a 1, and then jumps to 29. What it means is that at the lower pressure, things are gases in the gas phase, so the density is small. And then when the pressure is increased to this point, it becomes liquid. So the density jumps from 1 to 29. Okay, so there's a big transition from gaseous phase to the liquid phase. Now, if you limit your analysis in the gaseous region, what you get is a curve, a straight line. Okay, so this is the if you your analysis is inside the gaseous region, you get a straight line. Okay, then you get the slope as the first coefficient, and then you have a very small deviation from the line. And this is the reason why all the prior data gives very small third Virial coefficient. Because if you restrict yourself to the gaseous phase, at that temperature, when the pressure is low, the gases is still very almost ideal. Okay, so the behavior is very linear, and you get a set of second coefficient and third coefficient that way. But if you include all data, as a good person should do, then you get this curve. Okay, so you get all these 10 points here, all compressed into this very small region, and then in the liquid phase, you get many more data. Trying to fit this curve by regression analysis, you get the different equation. You get a different. So the second coefficient gets very big, and the third coefficient is also getting very big. Mm-hmm. And they are just too big. Okay, and if you notice, this curve doesn't cover the linear region very well. Mm-hmm. Yes, yes.
Is that anything significant? You know, because I think it's the minimum goes down to minus. I can't see it that.
Yeah, right.
Is that a significant point?
Not necessarily.
Not necessarily.
Yeah, I think the coefficients is what you look for.
Okay. Because the reason why I'm saying because I noticed that you don't have any data points.
No,
negative.
No, there's no data point there because the density doesn't go negative.
Oh, yeah, sorry.
Right. These are real gases. Okay.
I think the density in my head went negative.
Yes.
Yes. Okay.
Yes. So
that'd be like an unstable region then.
Yes. Negative is not stable. You know, the pressure never goes negative. Okay. Just like temperature doesn't go negative. Unstable, you know. So if you include all the data, you get this curve. The best curve that I like, and I think that the curve which gives the correct, from my point of view, correct equation of state is this curve. If you just take 1 point in the liquid region and do the second order regression analysis, this equation is the one I like. Okay, And I think this is the correct equation for the Virial equation of state. Okay, so you see here, the problem is that the analysis, the result of analysis depends upon the range you pick. So there's no objective ways to determine, who's right. Yeah, people are right. If they use this, they use this set of data, you get a very small third Virial coefficient. Now, if you use this one, you can get the very big coefficients. But that, of course, doesn't mean very much. But if I pick only one, I got this equation. What about if I pick 2 or 3? Okay, you can cheat very easily. Okay, so this second order regression analysis, you can tell lies. Okay, and it's not the object. So the regression analysis depends on the range of data when selected, and results were not conclusive. You cannot use regression analysis to support your argument, because then you have to justify the range you select and then da 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 da. Okay. So this regression analysis, I can get my data from there, but I have to substantiate it from with other methods. So the second method I use is to do residue analysis on Z. Okay, so we have the big table of compressibility and a big table of the density. So it is very easy for me to get the Excel to remove the constant, which is 1, and also the linear portion of the curve. Okay, so this equation can be solved or can be calculated very easily. Writing another array formula, and Excel will do it. So remove the constant part and linear part. What's left? Okay. Now, and there's lots of things left. Okay. But if I'm using a cubic Virial equation, after remove the constant part and also linear part, what's left will be only the quadratic part. And if I divide the residue by the square root of density, I got C. I got the third Virial coefficient for the whole table. Okay. So that's what I'm doing. What I call the residue analysis. So this way I can look at the whole table and see how the Z behave when I remove the linear part and the constant. So here I need to get the slopes. So I have to first calculate the second Virial coefficient, which are the slopes of all these curves in Z versus rho. And Excel has this function slope. If you give it two rows or 2 columns, and it will calculate the slope using the y in this array and x in this array. So it will calculate the slope automatically. So I from the table, the Z table, and also the row table, I select one this row from the Z table, this row from the density table, and then ask Excel to calculate the slope. And if I drag this cell across a column, and I get all the second Virial coefficient for at all the different temperatures. So once I have this array of the second Virial coefficient, then I can do the Z minus 1 and the minus B times rho. Okay, and this array formula would just do exactly that. And not only, so this part is the residue, and then I divide it by the square of the density. And so after this process, and I get a table, which is the third Virial equation. So this is what I call the C table. This is a table of the Virial coefficients. And that's the Z. Remove the constant part, the 1, and then the linear part, and then you can see in this region, which is a linear region, the numbers get very small because I have removed the constant and the linear portion of it. And so it comes to this to the right. At one point, it jumps from a very small value to a very quite relatively high value. And this high value kind of persists for a couple of cells, okay? And then it increases again, okay? So this jump, after the jump, this value, if you take the first jump, the first value, or if it is already constant, or if it is still increasing, you take the second number. And that's a very good value for third Virial coefficient, okay? And then it continues, it increases continuously to the right. And that's the contribution from higher Virial terms. I'm only using the second term. I'm only using 3 terms, and but there are contributions from higher Virial terms, and they show up to the right. But I'm concentrating on the third Virial coefficient. I can get them from this table. Okay, so this is the second way of solving this Virial equation, or my cubic Virial equation, and to get the third coefficient. Okay, so this is the result of the slope. It agrees with everybody else's result. But the third Virial coefficient, now I inverted this. I invert this curve. So in the earlier one, I have this curve which drops down. Okay, and I invert it, and this one it goes up. Okay, continuously inverted, it comes down, and shows that it's highly correlated with the second Virial coefficient. But the nature of this residue analysis, you take out the linear part, take out the constant part, what's left is of course the quadratic term, but the noise came in also. Okay, when you subtract all these things, and the noise shows up. So these, I think, anything the experimental data has uncertainties, and these uncertainties shows up quite well. I truncated at 600 degrees. If I continue on, it jumps up and down, and the curve looks really ugly. Okay, but that's because when you are doing the residue analysis, noise becomes amplified, not really amplified, but the noise shows up, especially when the yes.
But the main point here is that that curve for the C residues, not necessarily, you can expect the noise from the data, but the main thing is it doesn't.
Yes, that's right. That's the main point. I showed you, and the second Virial equation and third equation, they kind of goes together. Okay. Of course, the B is negative, so it goes down a negative, and C is positive, so it goes up. But it's easy to invert the table, so you can see the correlation. Okay, I got my secret weapon in this third method. The Virial coefficient can actually be solved in closed form. Okay, in the saturation region. Saturation region is between critical point and the triple point. Well, gas and liquid come into equilibrium. So in this region, the saturation properties, all these argon studies, they include this table of saturation properties. And that's basically the density of vapor and liquid and the saturation pressure and at the various saturation temperature. So the temperature, you change the temperature between the critical point and triple point. And then at each temperature, the argon comes into equilibrium at a certain pressure, and that's called the saturation pressure. And the gas, if you heat up the gas, heat up the liquid will boils off, keep on, but the pressure keeps on the same until all the liquids boil off, and then the gas and the gas pressure decreases. Okay, so that's the saturation property. So you have a saturation temperature, saturation pressure, and the vapor density and liquid density. These have been measured quite extensively for many years, and so you have all these collected into different tables, and all the studies all have the P rho T table, and they all have this saturation table. And from the saturation table, if I assume using a cubic Virial equation, you see here we can write the equation P equals to RT, and then this Virial expansion and times rho. So this is cubic equation. Okay, at the saturation pressure under the temperature, the P rho and T follows this equation. So if we rearrange this equation to put everything to the left-hand side of the equal sign, and you have this cubic equation. This the isotherm. This is an isotherm. Must have three roots. Okay, must have three roots in the saturation pressure. Let me go back to an earlier picture to show you exactly what I mean. Okay, this is so under a particular pressure, if you draw a line, it will cross this this isotherm at 3 points. Okay, on the left, it's a liquid phase, and on the right, it's the gas phase. Okay, but it will cross it. It will cross the liquid phase from top going down, and then when you across the gas phases again, it goes up and then comes down. So these 2 points are stable points because the pressure, the pressure PV curve has a negative slope, and this is the stability. Okay, if you increase the pressure, the volume gets smaller, right? Okay, but this in the middle, it also crosses, but that point is unstable. When the pressure PV curve is going up, you apply the pressure and the volume gets bigger. That's unreasonable, right? And that's unstable. So experimentally, we have the liquid volume, and we can measure the volume of the gas, but you cannot measure the middle point because physically it's unstable. So this is the difference between theory and reality. We try to use an equation to represent the behavior of real gas. And so we have an equation, and equation has 3 roots, but what about the middle root? You cannot measure it. Physically, it doesn't exist. But theoretically, if you use the equation of state, there is a root there, right? So if you draw a horizontal line at the saturation pressure, it will cross the isotherm at 3 points. And that's the 3 roots of this PV curve at that particular temperature and at that particular pressure. Let me go back to okay, here. So this equation here from the cubic Virial equation can be written that way. That's a 3rd order equation. If I have 3 roots, and I can write this equation in this form, right? So if you solve it, if this equation has any solution, if you can solve it, you can of course solve it mathematically. But I thought of a nice way. If I know where they crosses, okay, where the curve crosses, so I get liquid volume, I get gas volume, and V middle, I don't know, okay? That cannot be measured, but I can write it down. Assuming that there's a Vm there, and I can write down this equation. And this equation, I can expand it. So I got the constant term, linear term, and quadratic term, and cubic term. And these 2 equations are identical, okay? So from this linear term, I can solve Vm. From the quadratic term, I can solve B. And from the cubic term, I can solve C. Okay, so if assuming we are using this cubic equation of state, by measuring the volumes of gas and liquid, I can solve B and C in a closed form. Vm can be solved from the linear term, and then from the quadratic term, B can be solved. and C can be solved. So this and the results. I'm collecting all the three my three methods, and then compare with this this result, which is in the literature. This red line is the second order regression analysis. My second order regression analysis, if I pick the all the data point in the gas region and then one more point in the liquid region, and I get the third Virial coefficient this way. This yellow curve is from the residue analysis. And then here at the low point, it's kind of varied, and it goes up and down really madly. So I cut it off. But everybody cut it off anyway. So yeah. And then the saturation property, because saturation is only that available between critical point and the triple point. So the data is actually from here up, and it just coincides with all the other curves. So here, you know, the third Virial coefficient should behave this way. It goes up and not going down. Okay, so all three methods. Of course, the regression analysis you can cheat, but the other method you cannot. Okay, but they all give the same curve. So I think this curve is wrong. All the 100 years of research has to be redone. Okay, and another thing I wanted to show how B and C are actually correlated. So we have B solved, and we have C solved. We just take a ratio because B is always negative, so we put a negative sign there, and you can solve it. You see here, the C is the product of all three volumes. And then if you divide these three terms, you get the VL, these three terms. And these are actually density. Rho, density of liquid, density of gas, and density of the midpoint. And if at the critical point, VL, VG, and VM are the same. So they all equal to the VC. So at critical point, this ratio is 3/VC. And this is agrees very well with the experimental data. And if your temperature goes down, and these two splits out, and the V gas goes way up there, and VL stays pretty much at the same point, and the VM kind of floating in between. And if you get this one, rho G is very small. The density of gas is very small. And PM is a little bit, rho M is a little bit smaller, probably 10% of the liquid density. And the liquid density goes down to the 1/3 of the volume of liquid is generally 1/3 of the critical point, critical volume. So this relationship is valid over the entire saturation region. Yeah, and so this kind of proved the correlation of second and third coefficients. So my conclusion. The second and third Virial coefficients are highly correlated, okay? And the currently accepted the third Virial coefficients for argon and for other real gases are too low in the saturation region. Now, this does not mean that they are not valid, okay? Because they are valid only in the backdrop of a fully expanded Virial equation, okay? And the Virial equation, if you look in the prior studies, people got 40, people use 10 terms. And each term, the coefficient is temperature dependent. So, you easily can get 40 terms in a Virial equation, okay? Sometimes more. So these guys, they are pursuing numerical accuracy. So if you get a whole body of data, you want to write an equation which will fit all the data. Well, it doesn't fit, what do? Add another term, okay? So you just keep on adding until data fits, okay? So, with a very small third Virial coefficient, these equations are still valid because the higher terms will take care of the density and the high pressure. Okay. So, but if I insist on only using 3 terms, and the third Virial coefficient will have to account for the very rapid increase of pressure when the volume gets smaller. So that's, you have to have a very large third Virial coefficient, and to have the proper behavior to account for the liquid phase in equilibrium with gaseous phase, then these two Virial coefficient has to be correlated. Otherwise, otherwise you cannot get equilibrium. Okay. Okay, so the low third Virial coefficients are acceptable in a fully expanded Virial equation state, but not acceptable if the Virial equation is truncated to 3 terms. And it is because the third Virial coefficient generally represent repulsion among molecules. Okay, there were theories on the Virial equation, and they say, well, the second Virial coefficient accounts for the attraction between 2 molecules when they get close enough. And the third coefficient will represent the interaction among 3 molecules. And then the fourth term will account for 4 molecules, interaction among 4 molecules, and so on. Okay, but people never get past the second Virial coefficient because the third, it's the math just become intractable. So I think what I'm doing here is to try to represent all the repulsion potential using the third Virial coefficient, and that requires a very big third Virial coefficient. Okay, now I think this is the if the third Virial coefficient is properly determined, the complexity in the Virial equation can be reduced, because if you have all the weight collected in the first 2 coefficients, and all the other coefficients will get smaller and smaller very quickly. Okay, and the equation can be much simpler and much more accurate. Okay, so I I hope that I have proved that my cubic equation of state has great value in improving our understanding of real gases, particularly in the saturation region. Of course, in my prior talk, I can try to even extend it to the solid phase, which nobody was able to do. Okay, so in studying all the literature about the Virial theorem, Virial equations, I have derived my Virial theorem. Okay, now Virial equation is an open equation. You can extend it in any way you want, and so that's what people do. Okay, if the data doesn't fit, add another term. Okay, if data still doesn't fit, add another term in one of the coefficients, and so you can see this huge this equation of state just getting out of hand real quickly. You got I think one of the paper has 40 terms and coefficients, and some paper I saw more. Okay, so if data still doesn't fit, add another term in one of the coefficient. Repeat 1 and 2 until, if you are working on your PhD degree, until you get your degree, or until you get your paper published, or until you exhaust your fund. Yes. Okay. Now, another conclusion, never trust regression analysis until you know all the selected data. Okay. People cheat. And I think computers do not lie. Liars compute. So I think that put me into liars too. Yes.
It seems like we start going to higher coefficients.
Yes.
It smacks of, well, like in astronomy, you know what epicycles are. It was to describe the motion of the planets in the sky.
Okay.
Well, back in Greek times, they said, "Oh, epicycles, yes," and we do the thing. Yes, it fits. But the problem with that is, it's what are called kinematics. You're just taking a math model and fitting it to what the data is.
Yeah.
What you want to do is you need to do something that involves dynamics, which says why this is actually happening.
Exactly.
The basis of that.
Right. Exactly.
Right,
Exactly. Yeah.
And it because when you said 40 terms, I'm just going, ooh.
Well, that's Bartholomew doing.
Yeah.
Using circles to fit the data.
I know.
Yeah, right.
Yeah, but it's like, well, I fit it, but I have no idea what it means. So that would mean you need more statistical physics, and especially when you start getting into higher and higher densities, you might get to the point where quantum effects happen.
Yes.
Sorry to interrupt, but while you're answering questions, could you unplug your computer so Brad can?
Oh yeah, definitely. Yeah. Yeah. Right. Yes. Okay. Yeah, you're welcome. Let me. Let me turn it off. Oh well, let's not worry about it. Any more comments? Question? Well, don't worry. I was thinking of doing some manipulating the spreadsheet. If I click something and I can. Well, it's a lot of fun. Spreadsheet is lots of fun, and Excel can draw pictures. Chart, do very good charts. Yeah, and you see some of the pictures, some of the charts there, but the Excel is really nice. Yes. I think this the purpose of this thing is to try to get it published. I hope. I hope that now that I've filled up this hole in my first paper, this would get it accepted easier.
Are you ready to pass on the microphone?
Okay, thank you very much.
All right. Okay, Haiku Monthly. Let's talk about breaking news in fourth haiku. So first of all, we have DNA sizzling. We've got an interesting contribution that came in from Mr. 8 that looks something like this. Whoa. That's not good. 1 second. Let me. Technical fail here. I know why. Yep. You lie. They care about encryption. I'll explain why in a bit. Okay, come on. There we go. And ooh, we have our uber hot DNA strings sizzling away. If you look very closely, they're sizzling.
Folks with applied biosystems can see this.
Yeah. They're moving. Yeah, there's little. Which if you look back at it, isn't that amazing? Given that tiny little program. Okay. Yeah. Moving on from Russia with waves, we got an interesting contribution from our Russian friends. They were of course sending me editorial commentary in the comments asking me why I don't support RAD. I didn't actually know about RAD, and so that's the amazing thing here. Yeah, I know. I kind of fourth guy am I. So, anyways, here's what it looks like. Yeah. But that wasn't good enough. No, they need to make it even smoother and look like toothpaste. So they added a shadowy version that's got just a little more shading to it. Is it? I don't know. What's the right? That sounds better. Yeah. It's probably our fetch. Yeah. Says the guy who didn't know about it until yesterday. Silly me, pulling things off, duping them, and putting them back on.
Some people say it's something bang. Some people say it's something store.
Russia
Wave store.
That's odd. So, as you may have noticed, I'm using an intriguing slide framework I used recently for a talk at Fluent. Let me go back. I decided to push it to the limit by embedding the haikus inside of it, which seems to make it angry. So, yes. We have a new contributor, Monsieur Snell. He began with a simple haiku of this sort that looks something like this, but he followed it on. Oh no, this was not enough. He did flow, very nice and beautiful flow of particles.
Wow, looks like our guy.
You're imagining the surface that goes with. He then proceeded with a peppermint, and he actually learned about the transparency option, which caused quite a bit of hassle with the slides because then I had to embed an iframe and then have it be transparent to see the slide behind it. He then decided to go mechanical and produce a plotter. This is very succinct. Yeah.
Set the trigger.
Then his arrival introduced some synergy. So he produced a classic fractal, a Sierpinski carpet. But this inspired one of our longtime contributors, Darkstar AG, to produce the Sierpin clips based on his work. Oh. Okay. Of course, it seems that so the problem is that the slide framework loads all of them at once, and so it's sort of computing them in the background, and it's not very smart about which ones run when. Oh, hold on. This was okay. So we have a mysterious contribution. I believe this is a repeat. I got to thinking I've seen this somewhere before. So this is an example of why we need to track in the haikus what came from what, because this is lovely. I would love to know who the original author of this was, but somebody apparently cloned it and submitted it as an untitled and anonymous haiku. But it's awesome. So some variation on animal row with all the fun little whatnot. Isn't that great? Okay, and then some marvels from our friend Manway. Morph. Where, you know, again, I would never have imagined you could produce 3D shapes in this with these 2D shaders. So. Isn't that something? And it's really not that big. It's just a little bit too big to put up on the slide deck, but it's really not that big at all. And he's, of course, into your psychedelic madness because psychedelic, which will look more psychedelic once it gets going. There we go. And then a game of clocks. We started with Darkstar actually now, coming up with a simple clock that he's done in a very small amount of code. This is shockingly hard in this framework because you don't, remember, have the ability to plot individual pixels. You have to come up with the equations. This was followed, of course, by a rounded version of said clock.
It is the time of day.
It is the time of day, indeed. Followed by a spinning version therein. Looking like one of those twirly whatnots that you project on. But of course, the synergy reversed itself when Mr. Snail decided to bend time.
You had to show this just before lunch.
And as it happens, we're out of time.
Could I impose upon you perhaps next month to talk about how you got this?
Absolutely. There's a lovely framework that called Reveal.js that was actually quite fun. I used it for a talk recently at FluentConf in San Francisco.
Are the haikus out on the web, or are they on your machine?
So in this particular configuration, what I did was that the haikus are coming from the haiku site, and they're embedded in the slides, but the slides themselves are also posted on GitHub, so I was showing the page from GitHub with the haikus embedded in them. Yeah, if that makes any sense. So you have one website referencing another.
Thing. All of those things, we expect all of those things to work all at once.
Yes.
And your talk is going to actually appear on the screen.
Yes. It later occurred to me, particularly as I had problems. So you can embed one page in another with something called an iframe.
Yes.
And it occurred to me later that, of course, that trusts that everything in that iframe will work out great. In the future, if I were to do this kind of a slide deck, what I probably will do is pull the mechanics of the haikus out of the haiku site into the slide deck, so that at least there's not that one extra hop to hit the haiku server.
Make all of this stuff happen locally. Let's say you were to give a talk in Novosibirsk.
So
Said, oh, no internet coming.
Yes. Well, so intriguingly, the talk that I gave at Fluent. I actually did have my entire slide deck locally, and what I did was actually ran a local web server. And so in the event and so as it happened at Fluent, the Wi-Fi was terrible. There were, the big speakers in front of thousands of people, and oh, my demo required Wi-Fi, and the Wi-Fi is down. Sorry, my demo's not going to happen. But I was prepared because I had local slide deck and whatnot. But in this
these guys to be web programmers, and they have to have a local copy of the internet.
Yeah.
It's not the whole internet, it's just enough to wing it.
So yes, I can certainly talk about that next time.
Real internet, because that would be wrong. And the thing that's scary about this is that they get $1 an hour for most of the prison work, but for this they get $40 an hour. And they're going to try to get as many web programmers as they can that aren't going to be paroled anytime soon, so that they can make this $40 an hour. Because there is.
We're going to lunch now. See you later in the afternoon. Another deck. Bye.